So I'm starting the recorder anyway, and the first thing I'll do is to log into my DigiKey account and take a look at the stuff that I ordered. This was the whole order. Not everything is for this project, as you can see. Only the ones starting with an LP. These are the ones that are related to this project. But I can at least find out the part numbers, and then we can pull up the data sheets, and then we can talk about how to do that. Okay. So since you're here, we can start with the LED drivers. So we ordered 1, 2, 3.
I think there was just the 3.
Just the 3?
Yeah.
Okay. So we'll start with these 3 here. And with DigiKey, we can start up a... use a different window to look at the manual, to look at the part numbers. Do it like this. The data sheet. Okay, so in this case we have the ZXSC380. I think the other one is pretty close to this one. And then when you look at the typical circuit diagram, this is a, let's see, is that a boost? Yep, this is a boost configuration. In other words, the input voltage can be lower than the voltage that we need at this point. Is that consistent with your understanding?
That makes
it's a
sense.
boost. Okay. The efficiency is 80%, which is not bad. Hi, Jason.
Hello. That's pretty good.
What's that? That's pretty fast.
Yeah. Well, yeah, that's supposed to. I just woke up.
Yeah, I was referring to from the time you woke up to the time you get here.
Yeah.
Not the waking up part. Yeah, we were just going to review the circuit boards. I mean, the components that we got, so that we can get started with the circuit design part. Okay, so with this one, it's my only concern is this is a switching type of circuit, and basically the way it works is this voltage here, the incoming voltage, will go through the coil, and it will switch at this point. Okay, I know a better tool to do this with. So let's go ahead and open it. And this time choose. Okay, what's the name of that software? I cannot remember, but it's in my menu. Graphics. It is a software that you can use. Zerno, that's it. Okay, got it. There we go. It's a really great little program because it can do the same thing as a regular PDF viewer, but at the same time you can also handwrite or draw something over the document. So it's basically just like printing out the PDF and then be able to annotate it on top of it. So I think that's great for what we're doing here. Okay, so for this particular circuit, the way it works is you can basically have a current to go this way. So basically it charges up L1, which is an inductor. An inductor acts kind of like a flywheel. When you have it going, when you have current passing through the inductor, it wants to keep that current going. So that means when you cut off the current into pin 2, then all that current, which has to be the same amount at least for a short amount of time, now has to go through the LED to finish the circuit. And I should, the purple line actually goes through the chip to ground like this. So basically, just kind of alternate between these two. It will charge up the inductor. The inductor will build up a magnetic field around it. And when you turn off the purple line, then the inductor will the magnetic field will start to collapse. But the collapsing magnetic field will induce current in the inductor, and as a result, it will force that current the same amount through the orange line. And as a result of that, this current will be as much as it needs in order to complete the path to ground. And that's how a boost regulator works. And this chip here apparently can basically control the is it the current? Is it the current control device? You can take a look. Okay, let's take a look at the documentation here, and I'll zoom in just one level. That's too much. Zoom out. Okay, I think I can set to zoom to. Is probably just right, exactly. Okay, so in this case, you can have a low incoming voltage. See, the input voltage can be as low as 1 volt. Okay, so that's great because we now do not need to depend on a higher voltage as the input voltage, but they can drive white LEDs. If you look up the documentation somewhere here, I think it is designed to drive white LEDs, and white LEDs have a higher voltage drop across the diode, which is what this chip is designed for. Now the only thing that is not so good for our application, especially for the purpose of the red LED. Now you're in charge of not the red LED but the IRED. Okay, so for the IRED, there's only one thing that is my concern, and we have to try out to figure out whether that's going to be a problem or not. Is let's take a look at this picture here, which is a screenshot from a oscilloscope, and let's see, channel 1, which is the lower one, is the LED current, and the upper one is the voltage pin of the V out. Okay, so we want to track either one is fine. Let's go ahead and track the LED current, which is this one here. So we are tracking these lines. Now the problem with this is it is pulsing. It is not illuminated at a constant brightness. We cannot see it for sure because our eyes are very slow reacting. We can only see things maybe that is refreshing at a lower rate. Anything that's faster than 20 times per second we cannot see. And so now the question is the Wiimote going to see the on and offs? Will it misinterpret these as clicks? So the question is, based on the timing, what is the time between the pulses? If I'm going to measure this time here, what exactly is this amount of time? That's the question. Now that question actually can be answered if they give us enough information in this picture, but they don't, because I can't see. Okay, let's see if I can zoom in some more. I don't think it's a matter of whether I'm zooming in or not. Oh, okay, it is a matter of just zooming in. Okay, we are looking at 1 microsecond per division. In other words, when you look at this time interval here, from here to here, that's 1 microsecond. So that means, between the pulses, we have 1, 2, 3, 4, 5, 6, 6.5. Let's call it 7 microseconds. 7 microseconds is a really, really short amount of time. I think the Wiimote will not see the pulsing either. It will just see it as continuously lit. So I don't think we have an issue, but we have to implement the circuit first just to see whether it becomes an issue or not.
Are there specs somewhere? Well, I'm sure there are for like the Wiimote as far as.
I don't think the Wiimote has any specs released, of this sort, because it was never intended for people to create their own source of infrared. I don't think it's going to be an issue because people have used candles, as a source, and candles definitely flicker, and it works fine with the remote. And I think with pulses this short should not be an issue either, because when you look at, let's say this is 10 microseconds, so that we can do the division more easily. This is 100 kilohertz. 100 kilohertz means we have 100,000 pulses per second. And that's really fast. I mean, that's faster than most modulation frequencies, and most cameras cannot capture that kind of frequency either. So I don't think we have any issue with this type of pulsing, in the context of how we use our IRED. So that's good. This is good news, because I think because of the short amount of time, of the quick pulsing. It's not. I don't think it is going to be an issue. So let's reset this back to 120%. And here we have some diagrams correlating the supply voltage to the LCD current. And then we have supply voltage. It depends on. Have we decided on what type of battery and how many to use? Because last time I think what was left, I don't remember what was the conclusion, what was the decision.
Really have a conclusion.
Okay, but I think we were talking about 2 cells or one.
No, one.
One cell.
See, I don't know. I thought we were talking about just one.
Okay, well we can play.
Space is concerned and form factor.
Okay, we can play out the scenarios, because I think this is one of the consideration when we have to decide, what is the voltage of this thing. And instead of hand drawing lines that are not particularly straight, we can use rulers. So if we use one single cell as a rechargeable battery, the nominal voltage is 1.2 volts. So at 1.2 volts, we are looking at this line here. And when we look at this line, the colors are based on the value of the inductors. So let's zoom in a little bit. Oh, I like this tool. I think I have to start to use this tool a little more in my classes now. And I can save everything too. I mean, I can save everything, as another PDF or as a Zerno file, upload it. And Zerno has a Windows port. So if you download the Windows port, you can just download the file and reopen it, and everything like this shows again. Okay, so if you look at this, if you want to control the amount of current, you don't control anything except you use the inductor value to control that. The higher the value of the inductor, the more current average it is going to pass through the IRED. So in this case, if we use a 100 microhenry inductor, then you have up to about 13 milliamps passing through the LED,
Yeah.
which is not bad, because this is one way to control the amount of current that we are passing through the IRED. Yep.
So this would be run straight from the battery. It wouldn't be past the voltage regulation.
That is correct. It does not go through the voltage regulator, which is better because if you go through the voltage regulator, the conversion from the input voltage to the output voltage of the regulator, there's an efficiency loss right there already. And then you have to do the control, then you have to control the current by a resistive device. So that's another efficiency loss. This one, you pay the 80% or the 20% efficiency loss, and that's it. That is all that you're paying.
So the regulator is only for the MCU?
For the MCU and also anything that requires a constant voltage. So the MCU is one, and then I think the proximity sensor is definitely the other one.
Oh, okay. All right.
Because the prox sensor has an op amp.
Right here, right. Okay.
Yeah, the prox sensor and the proximity sensor and the CPU, they should have the same rail, because the value that you read back in software is a ratiometric kind of number. So if the two systems are powered from different voltages, then at some point they would drift and they things just won't work out anymore. Now this is not a whole lot of current. I mean, 13 milliamps is not small.
Yeah.
but it is also not 20 milliamps. I think the IREDs can handle up to 20 milliamps continuously. So the other solution is to change the voltage, the supply voltage of the system, to 2.5 volts, which is a little bit too much in this case, unless we use the blue line, which is a 22 microhenry inductor.
I was looking over these with Eric a couple days ago, and he was saying that was sort of the reason that he also chose the 383 to work with, because it gives more current with a lower inductor value. But he said we might be able to use this if it turns out that we can get it to run on a lower current. So
well, there are other solutions too, because we can use several IREDs in series. Because this chip is designed to drive white LEDs, which has a diode drop of around 4 volts.
Yeah.
Infrared LEDs only have a drop of 1.4 volts.
Yeah.
So we can string 3 of those things in series, and it will still be able to drive it at 13 milliamps. So we have 3 times the brightness of one at 13 milliamps. So that way we can amplify the amount of actual infrared emitting out of the device without having to change to a higher voltage battery system.
Okay.
So in other words, if you look at this picture, if I draw a picture, that's basically using. Oh, I forgot I haven't changed my tools. Change back to it. Okay. Here's my regular tool. Default pen. Okay. So we are basically talking about 3 diodes in series. So we can have 3 of these things in series. So the total drop across the entire series would be about 4 volts or so. So that way, even though it's still 13 milliamps, the brightness or the amount of infrared energy emitted will be 3 times of a single LED. So definitely we can play with this because a white LED has a voltage drop of 4 volts already. So this is doable.
Okay.
The only problem is how do we fit 3 of these things?
Yeah.
They make surface mount components too. So if we need to, we can consider a different package instead of using a 3 millimeter type of LED. We can choose a different type of LED.
Okay. So they make them smaller than that?
They make LEDs that are tiny. They make surface mount LEDs.
Okay.
08, 05, or even smaller. So they make really tiny ones. The question is how do we make that face the surface that is going to reflect the IR energy? That's the question. How do we make that happen? But the other thing is when you are drawing something. Okay, now this part we cannot capture using the screen capturing software. Is when you draw something like this, and your remote is on the side, picking it up. Do you want it to actually capture just the reflected energy dispersed because of the surface? Or do you want to light up this part of the light pan, the tip of the light pan, so that way the remote is actually directly picking up the light that is coming from the tip of the pan? That's the question.
I think just the surface. Just the surface, right?
Well, but the surface has, there are disadvantages to that. Because if you're just picking up from the surface and you're basically pointing the light, to the surface, and then depending on the dispersion of the surface to reflect back to the remote, a lot of that energy is dispersed into La La Land and it's not picked up by the remote. Whereas, if you light up, the tip of the pen itself, possibly more of the energy is actually visible to the remote. I don't know. That's a question.
Is that more of a software side, like the actual whiteboard software?
No, it's not the software. This is basically just physics. What is a better way to organize the IREDs so that from the perspective of the remote we can pick up as much light as possible. That's the question. Okay, if I draw a picture of how we intended.
I get it, but it's just
Okay, this is the reflective surface, right?
Right.
So right now our idea is, this is the light pan, and then we have, IREDs, here. The IRED will shine onto the reflective surface. And because the surface, if it's a mirror, it will never work. But because it is not a mirror, it has a dispersion, kind of pattern. So all this energy will disperse into, basically, 180-degree, kind of pattern. And our V mode, somewhere probably around here, will pick up, part of the reflected energy. So that's our current plan, is to do it this way. This is how all the other light pans work. But the alternative is basically to have the IRED to point to a side and have this part here to be a dispersal type of plastic, and then you have your V mode out here to pick it up. So in other words, we can have it so that we don't shine on the reflective surface at all, and have all the energy to face backwards. Instead of using the reflective surface to reflect the light, we point the LEDs actually can either sideways or even backward a little bit. So that way, the V mode can pick it up, can more easily pick it up. So that's just an idea. It's not we don't have to do it this way, but that's one potential way of doing it.
But wouldn't that cause? No, I guess when you initially calibrate the.
Calibrating.
Like, okay, so your hand's going to be off a little bit, so the angle that it's going to see, it's going to think it's further, and then it's going to want to put the mouse slightly to the right. But once you initially calibrate it, it's going to compensate for that, so with battery, right?
Correct. Yes. So just ideas, because this gives us a little bit more options, because now we can instead of using one super bright IRED, we can now have disperse it into a ring of smaller IREDs, but we can drive it each one with less current, because now we have basically just a ring of these IREDs, and from the perspective of the V mode, it just sees one single dot, because the ring, even to us, is a ring with the individual elements, but the V mode is far enough that it will just see the whole thing as one single source of infrared. So just an idea, we can throw it out and see if whether it's a good idea or not. Because doing it this way means that we can actually use surface mount IREDs. They're very small, and we will have a lot of flexibility when it comes to placement.
What's the cost difference usually?
Oh, let's
Are they
find
more
out.
expensive or less, generally speaking?
They're not expensive. They're not expensive. IREDs that are surface mount are typically fairly inexpensive. Let's go ahead and check it out. Okay, we're looking at optoelectronics, high brightness power modules, infrared emitters. And let's go ahead and look for surface mount. And they make right angle types. I don't think we want the. Well, let's go ahead and take a look. Let's take a look at all of these. And we only want to look at stuff that is in stock. Oh, okay. Okay, so now we can, control the maximum forward current. Let's pick the ones that are relatively small. So we are looking at, these have a fairly small view angle. We don't want those. We want something that has a wider view angle. These ones are not specified. Let's take a look. That's not cheap. That is not cheap. 6 pages. Oh, that's all right. We can sort by price. Unit price. That's still not cheap. PLCC2 is a pretty big, component. Must have something to do with infrared emitters. What did I do wrong? Are we sorted by unit price already? Yes, we are. No, we are not. Are we? Low to high. And we are not going to order 5,000, I don't think. Let's control how we're going to get the parts. We'll use cut tape. We'll do digireel, and let's just consider those 2 options.
I think when you went back, you deselected the surface one.
Did I? Wavelength? Well, I don't know exactly what is the optimal wavelength. Do you remember? Is it 880?
940 or 950?
940, 950? Do that. And now we want to sort by increasing unit price. Sorting in stock. Okay, 26 cents for this one. Non-standard SMD is fine because we are designing our own PCB. And the view angle is 120, which is great. Because this way we need only 3 to cover 360, and if we can somehow make 4, then we have good coverage from all angles. So let's take a look at this. Helping. Let's look at the data sheet. So this thing is the size. Let's see, where are the dimensions? So we have 1.25, this is in millimeters, by what is the other dimension? It's pretty tiny. This is 1.25 millimeters. That is tiny. It's 2 millimeter by 1.25 millimeter. And so we're not going to waste a lot of space on the board for something like this. That's for sure. So I don't know how the other problem that we have with something like this is how do we solder that, or how do we orient the circuit board to utilize something like this? Because the circuit board is flat. Okay, the circuit board itself is flat like this. We can definitely put one on top and one at the bottom, but that doesn't give us the 360-degree coverage that we need, because each one is only going to cover 120 degrees. So we still have some angles that are not covered. So I think the solution to this is to have another circuit board on top of this one. Okay, if we can have something that looks more like this, then we can easily get it done. Because now we can put one here, put one here, put one here, and put one here. So this will give us the coverage that we need. I think there will be, we can make it work. It's just not, with one single board. The other circuit board, we can attach it to the first circuit board just by using a right angle header attachment. So that can be done too. What do you guys think?
Seems really complex.
Yeah. Just thinking that we'll look
okay,
something
so
like that.
It just needs a little header here and another little header here. This is the main circuit board with all the other components
Right.
on it. Oh, I can make this simpler. Okay, this is our main circuit board. Okay, on our main circuit board we'll have, let's see how we want to do this.
What about if you use like a right angle surface mount? Would that
Right
be-
angle surface mount. Let's see if they have one part for that, because we can just combine this with one that can do a right angle. Okay, so we definitely want to remember this part number. And where am I going to put it? Open a new topic. This is my log. SMTIRED choices. Okay, so this is real tiny 2 mm by 1.5. Is it 1.5 or 1.25?
I think it was 1.25.
1.25 mm. Okay, and then we want to take a look at other choices. Okay, surface mount 0603 is also really, really tiny, so that's really small too. But it's not right angle, I think. PLCC2 1206, that's pretty small too. But this one has an angle of 18 degrees, so it has a lens on it. Okay, now we see the right angle type. And here's one that is 77 cents each. So it's not particularly cheap, nor small, but, well, since we're here, might as well take a look. High power infrared LED, short switching time, infrared illumination for CMOS cameras. So that's what it's intended for. IR communication, optical sensors. I want to look at the package, dimension of the package. This one has a, okay, here's the package. That may be, I want to see whether it is even, whether it can be hand soldered. Looks like it can be hand soldered, because this is the contact point. So if the circuit board is here, we can just put a pad here, and the size is, what is the overall size? We are talking about 3 millimeters by about 3 millimeters by about 4 millimeters. So this is still pretty tiny. We can do it. This is hand solderable.
But we need two of those, right? One for
We
each
need
side.
2. Well, okay. Now we can have 4, right? Ideally speaking, we only need 3 120-degree, type of IREDs, but we can have 4. Okay. So what we'll do is, this is our circuit board, and we don't need a daughter, a smaller circuit board anymore. And okay, this is how we do it. This is a side-facing one, so it will cover 120 degrees this way. We'll have another one on this side, which will cover another 120 degrees here. Then we have one that is not non-right angle type, and it will cover 120 degrees like this, and have another one at the bottom here, which will cover the other 120 degrees here. So we will end up with some overlap, but that's fine, because at the edge of the 120 degrees, it's not at full strength anymore. So a little bit of overlap, is actually, good. It's a good thing to have some overlapping. So this way we can have 4 of these things, And I'm not sure whether the ILED driver can handle the drop of 4 of these things. So this is something that we have to test and see whether it works or not.
Yeah.
But this would be great because now we don't need a daughter circuit board. We don't, from this perspective of construction and soldering, this will be pretty easy. And the best part is, this is not going to interfere with the proc sensor. The proc sensor definitely needs to be lensed, and they need to be like the ones that stick out. And now, those two, can come out this way, and these are not interfering in terms of using the space. They're not even the same part anymore. So I think this would not be a bad option, at least to take a look at. So the way it's soldered is this is the emitter is actually on this side. So the emitter is actually on this side. So it's emitting like this out of the part, and this is the back of the whole thing. So it's actually wasting quite a bit of space, just for the plastic holder itself. But it has to be like this, because if they don't do it this way and just reduce the length all the way up to here, then it's not as stable anymore. This is more stable because it has a larger brace, to mount the whole thing. But I think this is not a bad option. I think we can definitely look into this and see whether this will work just as well as one bright LED shining on the surface, itself. What do you guys think?
It's definitely more complex, but if it's better, then whatever.
We might have to do this,
The whole everything, because that's going to change the design of the head and all that stuff.
It simplifies the design, if anything, because there's no alignment anymore. This way, once you solder it, it's done. It's when you solder the part onto the PCB, the orientation has to be right. I mean, it's fixed. There's no other way to do it. And it's not sticking out either, so that there are no pins to bend. So I think it's not a bad option. Definitely worth considering. So let me go ahead and copy the part number of this guy. And it's also a little bit more expensive. This one is 77 cents each.
How much are the IREDs that we're looking at?
Oh, the ones that
Yeah, the part that has already been found that we were.
I do not remember. Okay. But that, but the whole discussion stemmed, from the LED driver not being able to drive the current that we want to drive it at the voltage, at the battery voltage that we selected, because we want the supply voltage to be 1.2 volts. All right, let's go ahead and save this. Oh, it's not making a new folder. What is this? Let's save. Let's go to archive. Okay. Okay, do we want to save this one? Oh yeah, definitely. And this is another one. where's the other one? This is the 303, the 383. Let's take a look at this part here and see if the specification is better than the other one. So input voltage can be as low as 1.0 volts. The IC can start up under full load and operate down to an input voltage of below 0.9 volts. And it's a single or multi-cell LED driver designed for applications that require step up or boost voltage conversion from a very low input source. It generates constant current pulses that are ideal for driving single or multiple LEDs over a wide range of operating voltages. Has on-off. Now that's the advantage of this part here is you can control it from software because it says it has its own on-off switch. So definitely the 383 has its advantage because we can control it more easily from the software perspective. And this is the circuit diagram. Okay. Let's enable. That's the output. Okay, so in this case, the enable, this part here, is done by a bunch of input or photodiode array, and then the output is the LED. So the connection circuit is about the same. It's just that this is a test circuit, and it's designed to work with one single metal hydride cell, which is good because I think that's what Derek has been saying. Use, and it uses only one external inductor, just like the other part. So that's good so far. Input photodiode array battery charge input, and then we have ground, switch output external inductor LCD, and supply voltage general alkaline nickel metal hydride or nickel cadmium. Very good. Look at the electrical characteristics. So the input voltage can go from 0.9 to 3.3 volts, which means if we switch to a lithium-ion battery, this won't work, because lithium-ion batteries start at 3.5 volts. Nominal is 3.7 volts, so that won't work with this. That will not work with this part.
Would that be an issue as well with the 380? You think?
Yeah, probably so. The 380 probably share a lot of the this part here. Yep. Mean LED current, assuming LED has a 3.5 volt drop, can be as high as 40 milliamps minimum to 65 milliamps. So in this case, we need an LED that can handle that much current because it doesn't seem like we can control the current easily. And the switching frequency is 330 kilohertz, which is good, because the other one has about 100 to 130 or so. So this one actually has a higher operating frequency. And let's see. Enable input threshold. This is basically what is considered a 1, and this is not a problem. And then we have pictures here. Okay, this is the input voltage. If we're looking at an input voltage of 1.2 volts, we can potentially, by controlling the inductor value, we can get different types of output current. So we can use the inductor value to set the actual output current in this case. So if the input voltage is 1.2 volts, and we choose, well, they don't have anything in between, but you can just probably just do some calculations, like 13. Maybe 15 microhenry would be about, at this point, which is 20 milliamps. So we can experiment with that a little bit, just to see what is the proper value for the inductor. But this is a better part. It can, it can handle more current. And then we may be able to use the part that we have already originally specified, and we don't have to go for the surface mount part. So this is not bad. And the pulsing looks like this. According to this, we have 500 nanoseconds per centimeter. Well, that's not helping because I don't know what a centimeter is in this picture. I think it is per grid. So basically from here to here, we have 1, 2, 3, 4, 5, about 6 divisions. And each division is 1/2 of a microsecond. So we have 3 microseconds between the pulses, which is consistent with the 330 kilohertz that they claim. So this one switches even faster, so the chances of the Wiimote not being able to pick it up is less. This is a better part. Great, excellent. So I think I'm inclining to test this one first, because if this one works, we won't even try to work with the other one.
Yeah.
This is a better part because it has one dedicated input pin to control the on-off operation. So I would definitely vote for this one first. Great, excellent. Are there any questions? I think I made at least 2 of these prototype boards already. Eric has these prototype boards.
Oh, okay.
Yeah. So this one already has one already done. And according.
What about the third part that he picked out for the driver?
We can take a look.
Okay.
But I want to show you, what kind of circuit you will need in order to test it. This is pretty much it. This diode, is not necessary. It helps to reduce the flickering, but I don't think it is 100% necessary here. It just reduces the ripple.
Okay.
Okay, so we can try with and without. The only problem with including this particular diode here is the efficiency will go down, because there's always a diode drop across this diode tube, and then plus you have, but it does make it more stable because you have a diode and also a capacitor to average out the current passing through the IRED. So it may be a better way. We don't know. We can give it a try. But we don't need a whole lot of external parts. So the inductor value that you need, according to this calculation here, assuming we use one single metal hydride cell, the inductor value that you need is going to be maybe 18, 16 microhenry or so. So I would try, something around there, just for starters. Very good. So we got, pretty much, this circuit designed. It's just a matter of testing it.
Yeah.
Any questions? No questions? Now, Hardy, did you pick up one of the hardware components?
Yeah, the
Regulator?
Regulation and charging.
Regulation and charging. Okay, let's take a look at the regulation circuit that we have ordered so far. Nope. No. Okay, we have a DC-DC, we have these 2 as boost regulators, and I think I got these soldered as well. I have 2 of each soldered, and let's take a look at one. I think these 2 are fairly similar. They're not identical, but they're pretty close.
The only thing that I saw that was different between the 2 was one of them used pulse width modulation, and there was another thing that was slightly different. But otherwise, they're essentially the same.
Okay.
At least from what I saw.
Let's take a look at the part. Nope. Well, this is pretty good. It can handle 800 milliamps of typical input current, and then the output, low input voltage is 0.35 volts, and the typical output is 3.3 volts and 1 milliamp. Adjustable output voltage range from 2 volts to 5.5 volts. Maximum input voltage, has to be less than 5.5 volts. So it's fairly flexible. I mean, you can give it a wide range of input, and you can program it to generate a wide range of output voltages. So that's pretty good. Low noise, anti-ringing control, over temperature control. So that's all good. And this is the part that we got. We got the SOT23 package. This one is really difficult to solder because it doesn't expose any tabs, any pads, so it's really hard to solder by hand. This one can only be done by a reflow oven. It's not something that can be done by hand. 1, 2, or 3 cell, alkaline or nickel metal hydride, so that's good. Single cell lithium ion to 5 volt converters, and so on and so forth. And the circuit diagram, typical circuit diagram, looks like this. And I think this is the one that we want to, evaluate, because the input voltage range is what we, it matches what we want, and the output voltage also matches what we want as well. So if you are going to implement this one, I would just go with these values. The only thing is, when you specify the input, this is not as critical. This one you can just pick, just about any capacitor with this value, should be okay. And then the output is the one that you want to be a low ESR type, because it helps to reduce the ripple. It stabilizes the output when you have a better capacitor as the output capacitor. So not a whole lot of components. You need an inductor. 4.7 microhenry is a very typical value. You can find lots and lots of parts like that, and that's good. This is a good part. And then you need to have this particular divider bridge, because the feedback has to decide is the output voltage what it needs, and that's why you have a divider bridge here. And these values will help set the actual output voltage. Okay. So any questions about this circuit? I don't think the input, the input capacitor value is really that critical. So you have a variety of choices here.
I had made a schematic of that on the forum and gave like a little description of everything. And I had understood that the inductor was merely to smooth out and filter the voltage a little bit, but then Eric said that it's more for, it actually helps a lot more with the voltage regulation.
It boosts. This inductor is for boosting the voltage. Just like with the other ones.
Yeah, when you were talking about it on the IRED circuit, I kind of started to understand.
So basically, when you charge it up like this, it charges up, the capacitor, and this thing will switch it to ground directly like that. And obviously, ground, this completes the whole circuit. When you turn off this, when you turn off this switch here, and I'll use an orange line to represent that. When the internal switch is turned off, so it doesn't go to ground directly, the current will still have to go through the inductor. The inductor will still want to maintain the same current, but instead of going to ground, what it will do is it will go to the load of the system. And then the load of the system, whatever it has to do, will have to go to ground and complete the circuit. So that's why it has the functionality of boosting the voltage, because the inductor will basically force the same amount of current through, even though it is not a straight path to ground anymore. Now, the heavier the load that you have here, then the higher the switching frequency, because it has to switch a lot more to keep charging the inductor and then discharge the inductor, charge the inductor, and discharge the inductor. And that's why in this case, it is very important to have a good output capacitor, because your output capacitor really helps to smooth out everything. And let's go ahead and choose a 10 microfarad capacitor and see what kind of choices we have.
So that was the other thing, was that I didn't know what size to go with everything, so I just kind of went with, I don't know what size actually.
You mean the physical size?
Yeah. I didn't know if we had any standardization we wanted to.
I have always had good luck with the Panasonic type. They're surface mount, and they're really, really small, compared to the alternatives. Let's go ahead and take a look. A 10 microfarad capacitor is really small, on the circuit board. It looks like a little tin can, on the circuit board. Let's take a look. we want a 10 microfarad. So let's take a look at capacitors. And the value, with the 10 microfarad value, we cannot be looking at, ceramic, because ceramic don't have values, up to that high. You basically have to look into, I think tantalum, has, values like that, and then your alternative would be aluminum. This is an electrolyte type, capacitor. And since we already know the value of the capacitance, we can just, choose that first. So 10 microfarad. And we want to limit ourselves to cut tape and digit wheel. The other ones are, basically for really high quantity type of orders. So we'll limit ourselves to in stock as well. So that should significantly bring down our choices. Voltage rating, since your output voltage is only 3.3 volts at the most, I'll just select the first two. If you pick the other ones, they're not necessarily more expensive, but they will definitely be bigger. So for the size consideration, we'll just limit ourselves to 6.3 volts to 10 volts. And well, that pretty much gives us all the possible options. And many of these are bipolar. And here's a polymer type. Nice. A polymer type is nice, because it can actually switch current a lot more effectively than an electrolyte type. And according to this is also a surface mount, a flat surface mount part, which is kind of cool. And the size, did they mention the size? The size is not tiny. It's 7.3 millimeters by 4.3 millimeters, so it's kind of big. So from that perspective, it doesn't look very attractive because the other ones are smaller. They have a smaller footprint on the PCB itself. What are we looking at here? The height. The height is not really important because when you look at the light pan, the inside of a light pan is a circle. So this is our circuit board here. So we do have some space, in the middle. Now on the side, we cannot use thick components anymore because the side doesn't have that much space vertically speaking. But we're still talking about up to 5 millimeters, which is not that big. And now we can take a look at the price here. This one is expensive. I think this is our polymer type. Let's take a look at this specification. Okay, so rated ripple current and frequency. This is basically the frequency that it used to test the capacitor, and it's basically switching at 100 kilohertz, to test the part, in order to get the numbers that are following. And right here, the ripple current is 1.4 amps, which is much more than what we need for our application. And we have an ESR rating here. The ESR is equivalent series resistance. The smaller the number, the better. And this one is measured at 55 milliohms, which is really, really good. I mean, the smaller the number, 55 milliohms is basically 0.055 ohms, and that's a really small value, which is good. So that's why this is expensive, because it has all these traits that makes it a very good capacitor for not only this kind of application, but for many also other applications. The endurance is only 1,000 hours, which is not bad, because most of the other capacitors are about the same. Let's take a look at the cheaper one, maybe this one here, and see how it compares. Because what we want to do is to look at different options and see how they compare, look at all the numbers. And this one is a tin can type. So let's take a look at the tin can. Do you guys remember what is the rated voltage of this one? It's the second item. I can tell right away this is an inferior, it's a 10 volt, but you can look at the 25 milliamps, that's the ripple current. So you can look at the difference, 25, 25, 25, 1.4 amps. The 1.4 amps is, by far, much better than the alternatives. If we look,
what is the ripple current doing again?
The ripple current,
the most that it can take, or what is that?
it's basically at the test frequency, which is 100 kilohertz in this case. If we keep charging and discharging, charging and discharging the capacitor, what is the highest amount of current to use to charge it and discharge it before the capacitor starts to overheat or work out of its characteristics? And 1.4 amps is a lot compared to 25 milliamps. So we don't have anything quite like that, except for this one. This one has 2.2 amps, which is even better. But I don't think we need anything, of that magnitude.
Right.
But 25 milliamps is not enough either. So we are looking at. Okay, let's see. This one has a higher ESR, or equivalent series resistance, of 220 milliohms. All of the other ones have 55 milliohms or so. So if we really need to make a compromise, okay, I think this would be a nice compromise, because the size is also not too bad. Okay, it's about the same size in terms of footprint as the tin can, except this one is all flat. So I think this would be a good choice. The 92 cents one would be a good choice, because it's less expensive than all the other ones. But given its performance, it's a good trade-off. So I would pick this one. Oh, this is not a polymer type. It is a polymer cathode. Okay, it is a polymer type. I would pick this one. This is a good trade-off. We are basically looking at this entry here. It's 4 millimeters by 5.2 millimeters in terms of the footprint of the part. I think that's a mosquito. And if you look at the specifications, what is it? 10 volts. The ESR is 220. And the rated ripple current is 0.7 amps, which is still good enough for what we are doing. So this is a good part to use. Let me just add it to the collection. So is that helpful? Is that good? Okay. So next we can look at the inductor. Was it a 4.7 microhenry inductor?
I think so. It was either 4.7 or 10.
Okay, let's take a look. It's 4.7. 4.7 is a more regular values. I don't understand why, but 4.7, 2.2, 10, those are typical values. It's not like 10, 20. It's 10 and then 22. And then I think there are no 30s. The next one up is typically from 22, it goes to 47. And then from 47, it goes to 100. So they don't jump in steps.
They're like powers of 10 then?
They're not powers of 10. They use some sort of multiplier.
10.
I think it's a power. It's
22, 47, 100, right?
sorry.
If it's 22, 47, 10, and then 22, 47, 100.
Yeah.
That's.
It's cyclic. Yes.
Yeah. But on the inductor, when I was reading down at the where they had some of the calculations and stuff that I figured out, it was saying that they recommend a minimum of like a 4.7, like a 10.0 is, or a 10 is more standard or something like that. So I wasn't really quite sure as to.
You mean for this inductor?
What to go as far as like safety. You know?
For this inductor here?
Yeah.
Okay, let's go ahead and look at the inductors. Okay. Let's go ahead and look up inductors. Because I can show you, what type of metrics they use to characterize inductors. Inductor. Fixed. And we just look for that particular value, which is 4.7 microhenry. And then we want to look at only cut tape, digit wheel, tube, and in stock. Okay. So when you look at this, they have saturation current, temperature rise, current temperature rise, and also current. Now, the more current it can handle, the better usually, because that means the internal resistance is lower, and then you get a better output. It doesn't have as much a ripple. But beyond a certain point, there's no return anymore, because our inductor can only has to switch at a certain rate. So it depends on the actual load that we put into the system, and that pretty much determines what kind of current will be pumping through the inductor most of the time. So in this case, you can do some calculations. We have to look at all the output devices that are powered from the 3.3 volt rail. We have the proc sensor that's powered from the regulated voltage. We have the processor itself. So let's say the processor is running at. Do you remember what is the current of the processor at 4 megahertz? I think it's around.
It's like 2.7 or it needs 3.3. Or no, we don't have the one that does 4. We have the one that does 10 or 20.
10 or 20?
Yeah. Because the one is like an 87V and the other one's just 87 or 84V and regular 84.
Okay, let's say it's 20 milliamps or something like that. That sounds like a reasonable number. And then we have the red LED. The red LED has to come from the regulated source because we want it to be flat. We don't want it to be pulsing. So that one has to come from the regulated source as well. But it's not on all the time. It's on only for a very short amount of times. So the only other thing that will take up a lot of power would be the op-amp itself. And I cannot remember how much current the op-amp consumes. It's not much either. So let's just say it's 50 milliamps. Now 50 milliamps doesn't sound like a lot. 3.3 volts at, let's say 50 milliamps. But the input is much lower. The input is only at 1.2 volts or so. So for the calculation purposes, we just say it is 1.1 volts. So now we need 150 milliamps at 1.1 volts. Okay, because of energy conservation. If the output is consuming this much power, then the input has to input as much power, and then plus we have the inefficiency of the entire system. So we have to divide this whole thing by the efficiency of the conversion. So we are talking about maybe 180 milliamps or so. That's the average current passing through, sourcing from the low voltage, from the input voltage.
I'm sorry, can I interrupt you for a sec?
Yes.
I've actually got to go. I have to meet someone to repair my apartment.
Oh.
So, have you seen Austin by chance?
Not today.
Okay. Well, I need to pick the soldering iron back up. You don't have any parts for me by any chance, do you?
No, I do not.
Okay, that's fine. Perfectly fine. Need that ironed out. So
I think we have pretty much decided on which IRED driver we want to test first. That's the one that we have that I have soldered already.
right, I just didn't want you to have something and me not touch base with you and leave without getting it.
Oh, okay. Yep, I think we're good.
All right. Well, sorry.
Okay, well, everything is still being recorded, I hope.
You're gonna be what?
Let me see if it's actually recording. Yep,
Like 5
it is.
minutes?
See here.
Okay, Eric's, can you wait 5 minutes?
Yeah.
I guess Eric has to go.
I'm gonna go touch base with an office here. I'll be back here.
Okay, so see you in a bit.
Sorry.
That's all right.
I kind of missed everything you just said there.
Blah, 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 blah.
No, but the visual part wasn't.
Okay, so we
I'll take a picture of it, and when I'm watching the recording, I'll like scroll down slowly.
okay, basically, sourcing from the 1.2 volt, source, we might need up to 180 milliamps, coming out of the nickel metal hydride, battery. Now, how much of that, actually has to go through the inductor? That's a question that I cannot answer because it depends on the characteristic of the switching of this, regulator. We can actually we may be able to find out if they have timing diagrams and stuff like that. Like actual. Oh, there we go. Okay, this is the picture that we want, because it's you're looking at the output voltage, and okay, let's take a look at these two pictures. Zoom in. Control plus. Okay. Control plus is to zoom in. Oh, that's control equal, so I need to control shift. There we go. Okay, so now we are looking at the picture, and this is only with, okay, this is 50 milliamps as the output of 3.3 volts, and 20 millivolts per division is the output. So we are looking at how much ripple the system has, how stable is the voltage. Okay, so we want to take a look at this picture. Because what I want to find out is, what kind of inductor should we pick? What is the current rating that is appropriate for the inductor? And then, of course, the other part that I have not done that I should have done already is actually just to read the text and see whether it has any recommendations. Because typically it usually has some sort of recommendation, like what type of inductor is appropriate for this type of application.
That's all underneath that, lower down.
Underneath?
Yeah, keep scrolling down. It gives you all kinds of information.
Device option. Okay, that's where we need what we need. Okay, output capacitor selection. So we're done with this part already. With this one. And oh, we can actually go with a higher value for the output capacitor, which may not be a bad idea, but it will take up more space on the board. And then we have inductor.
See, it lists their recommendations, but as long as we have the same
Specs, yes.
it doesn't really matter.
That is correct. If we have the same specs, then we should be good to go. Yeah, we may be able to plug these in, plug in these numbers, with DigiKey, and we may be able to find a part already. They may stock these parts. Have you tried to plug in these numbers?
The ones I did try, they didn't
Did you have?
I gave up after like 3 or 4 times.
Okay. Well, looks like we're looking at maybe a quarter of an ohm for the DCR or the DC resistance, and the saturation in current, has to be about, at the lowest is 0.68. So we can just use these numbers and switch back to this part here. So for the saturation current, we want it to be at least 700 or so, and we can work it up to maybe 2 amps or so. And then for DCR, okay, for DCR, the highest value is the worst case. So the highest value in this case is about 0.28. So I will just call that the worst case. So we'll start with 280 milliohms, and we'll work our way back down to, say, this part here. Okay, how many choices do we have? We still have a lot of choices. So that's, basically that's how I would, look at the numbers. You basically look at the recommended parts, look at their, specifications, and you just pick something maybe in the middle or, in the range of what is suggested. So that should be, fairly safe already. Basically any of these choices, would not be too far off, from what we need. So we can look at all these parts, and then we can sort by price, unit price, and we just go for simple. And we have some pretty small parts here. 1212 is a fairly small component, and the numbers are fairly decent. I mean, they're not the worst of the bunch. And if you look at the price, 37 cents each is not bad. So I would, use this method to, evaluate the parts and see which ones are appropriate. But it looks like, it's not going to be a big part. It's just that we have a lot of these little parts. The IRED driver circuit has its own, inductor, and then yours has its own inductor. So we have a lot of these little, components, and they all generate noise. So the other question is, is it going to have any effect on the accuracy of the proc sensor?
I have a question more on like selecting parts. If we're all using, like you're saying, she's got inductors, I've got inductors, everybody's got resistors. Should we try to standardize anything, or should we?
If it is possible.
Okay.
Okay. If it is possible, I cannot remember. It's not. I don't have it displayed anymore. I got the file saved though. I cannot remember the value of the inductor that we should use for the IRED driver. Was it 4.7? If it is, we can use the same thing.
But like if there's a range, like there's a range on all these parts, but if we can find something that overlaps for both of them,
yeah,
should we just go ahead and try to?
Yes, because then you can order it in a higher volume, which means you can lower the per unit cost. Yep, definitely. Okay. So any other questions regarding the regulator? I mean, I think that was the last component. And they even give you, a suggested layout of the circuit board. Now this is great, okay? This is great because a lot of times with switching regulators, the problem is people don't know how to route the signals. Okay, if you use thin lines and go through all kinds of paths, one, it will be noisy because every path with alternating circuit is basically an antenna radiating interference out of the system, which is not good. And the second thing is, with parts this small, a lot of times the heat dissipation is done by the trace. It's done by the copper on the PCB and not through the part itself. So if you have really thin traces to do all the interconnections, it may not give it enough heat sinking ability, and your part will overheat and die prematurely. But in this case, since they already give us the recommended routing diagram, it's done. I mean, this is what they have used for testing the parts before it rolls out of the factory. So this is great. We can design the circuit pretty much the same way like this, but making minor changes to accommodate the parts that we use. And that's the only thing we have to do is to customize it. But we can use pretty much the same layout as what is suggested here. That's great. And you can also see how the ground plane is used as a big heatsink. It's basically, if you look at the ground plane is this part here. If I use this color to lay out, so you have everything here all the way up to here. I cannot tell. One is the top layer, one is the bottom layer. I cannot tell which one is the top, which one is the bottom. The color is different. I think that's one ground. This part is not a part of it, I don't think. Can you guys see whether the color matches or not? I cannot see. The contrast is really low.
For what?
I'm looking at the continuous ground part of the signal. I cannot tell. I'm sorry.
So, which parts were you saying were connected, or you think may be connected?
Well, I want to borrow their recommended design of the circuit,
Right.
and I just want to find out which part is the ground.
The enable pin should be connected to the positive.
Yeah, the enable has a via, so this is not connected to anything. This is an island all by itself.
Well, that connects to the positive though, doesn't it? If you look at the diagram.
You mean the circuit diagram?
Yeah. Way up at the top.
This one?
Yeah. See, that goes to positive. Right?
Which part?
The enable pin, EN.
The enable pin EN.
That connects to the positive. And then on the opposite side of the capacitor connects to ground.
Oh, that's a constant on. That's just having it to turn on constantly.
Right.
But in the actual circuit, they have a via so that you can actually bring it to a signal to turn it on and turn it off.
Oh, okay. I see. Okay.
Yeah. So basically, but you can tell, this ground pin is ground, this is ground, this is ground, and so this is also ground.
Right.
So that way, I can spend some more time to identify, which part is the ground. But what I wanted to illustrate is the circuit or the layout is already designed to maximize, the copper area available to act as a heat sink for the components. So, which is great because this means I don't have to think about it when I design this part of the layout of the PCB.
Right.
Yep. So I think, are we doing okay with this? Now I'm not sure whether you really want to prototype this using a breadboard, because when you prototype it using a breadboard, you're not going to end up with an equivalent circuit that looks like or even remotely looks like this. You will have longer paths. And a lot of times, your conductors, would not have nearly as good of an electrical contact as a soldered, part on a PCB. But for the most part, you might still be able to test it. But if it doesn't work, don't get discouraged, because sometimes just because you have longer wires will change the characteristic of circuits like this enough to make it not work. So you can give it a try. I would give it a try to see whether you can get it to work. With a breadboard. Just to prototype it.
Right.
If it doesn't work, don't sweat it. It's probably okay. We just have to design it the way it is suggested on an actual PCB, and we should be good to go. So that's good. So we got the IRED driver circuit pretty much figured out. It will be powered from the battery directly, and it has an 80% efficiency. And then we use the second part, the other part, the second one that we talked about, which has a higher drive capability. So that would be the first part that I try to use, would be that one. And then this is, basically the power supply, the 3.3 boost regulator circuit. So we got two of these, things knocked out today. We got some components identified, and I haven't, uploaded that yet. Let me just upload it first before I forget.
there, Tag.
Okay, see ya. Study for the test.
Yeah, that's gonna be pretty much 30 hours a day.
30 hours a day.
Take up all my time. See you guys.
Did you post the links to last week's stream and stuff?
I might have done that. I cannot remember. Let me save this one first and look at the other one. 4.8.
What's the deal with that
Meeting.
million up there?
I noticed that.
What?
I was asking Mike what the deal is with that million up there. Is that Chase's doing?
Yeah, that's Chase's doing.
Okay, this is recording from last week, but that's from the week before last, right? Yeah, okay. So I might not have uploaded that one yet. I think I uploaded, I just did not put the link there.
It's a screen capture thing you did, unless you did something before that also.
The live stream.
Yeah, the live stream. We did something before the live stream, but I don't think it was anything significant. Yeah, so the live stream is the part that is actually useful. And is that already uploaded? Did you share the link already?
I didn't post a link, but
Okay.
it's on the website. So.
Yeah. Okay, so you guys know how to find the live stream link? Okay. And that worked out pretty good. I was impressed. I was impressed that it was able to upload that kind of quality, but only with a 6-second delay.
Yeah.
That's impressive. Yeah, but everything that we are doing today, they're all captured too. You're also doing the charger circuit?
Yeah.
Okay, have you identified the parts to do it?
No, I haven't looked at that.
Okay, do we want to include the charger? We do want to include the charger circuit into the whole thing, right? I mean, that's just handy. I think it is just handy to have that included. Have we identified parts for the charger circuit? No.
I don't think so. Well, no, maybe. I think you posted something on there, but I don't know. It's been a long time.
Okay,
Did
let's.
we go looking at a whole bunch of parts?
I think it was on
one
the
chip and everything.
discussion.
Yeah, we did.
So,
I don't remember when we talked about it though.
I think it's in the discussion forum.
In the discussion forum. Okay, there has to be a little bit of time.
Down a little more.
Okay, we got the proc sensor.
No, maybe not.
Maybe here.
No,
No.
it's probably not in there.
Okay, well, we can always look at it again. I have to go at about 3 o'clock, but since it's not there yet. DigiKey is just great. I mean, it's a very good tool to search for parts. I haven't seen anything as good as this. I mean, other sites that sell parts have something similar, but I think this is by far the best. Battery products. Battery chargers. I don't think those are chips. Power management, LED, battery management, that's it. Okay. So we want battery monitor? No. Charge management, yes. Solar, yes. Oh, okay, my light pen is running out of power. Need to go out and charge it.
Wouldn't that produce enough light? The projector?
That's what it was. It was all on the screen capture.
Yeah.
That's where all that information is.
Okay. So somebody has to watch it again.
Forget which one it was.
Okay, what is the supply voltage of USB? I think that's 5 volts, right?
Yeah.
Okay. Okay, we want surface mount. We want cut tape digi-reel. We want in stock. Okay, now we talked about the battery chemistry too. I think last time we talked about one that will work with all 3 types. Now since if we're going to use only lithium, nickel metal hydride, This is the only one that can work with nickel metal hydride. So we'll just pick that one. And here we have the chips. Sort by price. There we have it. $2.47. But this is a really hard one to solder, so I would not pick anything like that. This is one that I can at least solder this one. So let's take a look at this. Non-stock. Not gonna help.
Maybe it's in stock elsewhere.
Well, non-stock means they actually have it here, but once they are done with these 281 items, they have no idea when they will get more into in stock. So we should probably look at something that they keep in stock all the time. So this will be one that they keep in stock all the time. And let's take a look at that. The circuit diagram looks like this. And this one, I don't think it needs its own inductor, because a charged circuit usually does not need an inductor. And that's it. Pretty, simple. This one only works with lithium ion, but I think one that works for metal hydride should be down here somewhere. Diagram, application notes, right here. Logic control programming of control output current to 0 milliamp, 200, 500, or 700 milliamps. This is great. This means you can actually use software to control the charge current. I don't think we'll need it. Okay, I think we can just use one single charge current and be done with it. I want to see a sample circuit for nickel metal hydride, but I can't seem to find one. This is still lithium ion. Just read the description. Make sure that it can in fact charge nickel metal hydride. But this is lithium ion only, according to this. That's not what we want.
The LTC will. There was some stuff, some more information down at the bottom about metal hydride.
It's done.
Charging nickel.
Yeah, that last paragraph right there.
It also functions as a general purpose current source for charging nickel cadmium and nickel metal hydride battery using external termination, which is not something that we have. External termination means you have to make it stop at some point.
Right. And I was looking at like the Energizer and Duracell data sheets, and well, that's not going to know what but they are all recommending that you charge a
delta
metal
type?
hydride with watching the change in temperature versus the change in current or something like that. Or the change
You use constant current, and then you watch for the voltage change and also temperature change.
Yeah.
Yeah, because at the very last bit of charging, the temperature rise is going to be very sharp, and also you will see a dip of output of the voltage when it's done charging. So that's the delta.
Right.
And then you look at the temperature, because the temperature is the safety feature, because you don't want your battery to go, to get too warm.
Right. So we're pretty much going to need some sort of external termination, right?
Some of these chips, they have pins to connect to thermistors and all kinds of other stuff, so you can do everything internally without having to have the MCU to actually monitor the charging. So the question is, do you want the software to be a part of the charge control, mechanism, or do you want to kind of make it use a chip that is self-contained?
Sleep on it.
I mean, really, it doesn't make that much difference. Yeah, it's one thing, well, because it's going to have to be programmed anyway, right? Either the MCU is going to have to be programmed or the
primary charger chip to be programmed?
No, the charger chip typically does not need to be programmed. You use resistor values to set the charge current, and once you set the charge current, it will just look for the delta of the voltage delta, and then that will it will stop charging using that. So that's that's one thing we can do is to use that as a charge circuit. Let me see if what other choices we have in this list here. We have one from TI, this chip here, and it claims to be able to do lithium ion, nickel, cadmium, and so on. The input voltage is also at 5 volts. It is a little bit more expensive at $4, but let's go ahead and see what it can do. Can it do it without any help from the MCU? Safe management of fast charge for nickel, cadmium, nickel metal hydride, or lithium battery packs. So that's good. This implies that we don't need any external termination. The chip itself can do it. It's a programmable, non-monolithic IC for fast charge management of nickel cadmium, nickel metal hydride, or lithium ion batteries in single or multi-chemistry applications. Blah 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 blah. Depending on the chemistry, depends on the number of charge termination criteria. So this is all done on chip. It does not require an external mechanism to look at the voltage and say, oh, stop, it's full. So I would say this is a better chip to use, even though it's slightly more expensive. It even keeps track of, depending on the chemistry, provides a number of charge termination criteria. For safety, it inhibits fast charge until battery voltage and temperature are within user-defined limits. That's good. It's just a nice self-contained type of chip. It even has a status output, so you can hook up an LED to this particular chip, and it can indicate whether it's charging or not. So I think this is a better, higher integration part that we should use. Let's take a look at the circuit that you need to get it to work. State diagram. Is it a state diagram or a flow chart?
That was the state. Yeah, pretty sure.
Yep, it's a state diagram. The transitions are basically which voltage is higher than which voltage. But I want to look at the circuit, an application circuit. That's an application circuit, temperature monitoring. That looks complicated to me.
Yeah.
Document control stuff. Okay. Looks like somebody has to read something.
So do you actually have to build that circuit now?
Sorry?
You actually have to build that circuit to make it work?
Well, you have to add some external parts. We just have to figure out how many external parts it needs to get it to work. And I don't think it's a whole lot either, because if you look at the pin designation, okay, you have current sense input. We have this pin is needed to sense the battery current via the voltage developed on this pin by an external sense resistor connected in series with the battery pack. That's pretty easy to do. System ground, just hook it up to the ground pin. LED, it's an indicator, and I think it's a good feature to have the indicator, because otherwise, how do you know the battery is fully charged? So this is a very good feature to have. Battery voltage input sense is a sense simple resistor, resistive divider is good, so that's pretty easy to do. Temperature sense input. This is only if you want to. I think this is optional. So if we don't want to have a temperature sense input, we do not need one.
But don't we need that in order to charge a nickel metal hydride correctly?
If you
like,
want
all
to,
the-
if you want to fast charge it, yes. But if you want to charge it at a lower current, you don't need to monitor the temperature.
All the data sheets recommended that you use a temperature
Mhm.
pin no matter what, even if, well, not no matter what, but if you're charging it at least 1C,
Mm-hmm.
they recommend use the temperature. If you're using lower, like for just trickle charging, you don't need the
Well, 1C is already pretty fast.
Yeah.
Yeah, 1C means the whole thing is going to be done in an hour.
right.
Right. So we can use it. I mean, it's just a matter of how much of the circuit do we want
But
to
then we
use.
need what's it called? There you go.
Hmm?
Temperature sensor? Temperature sensor?
You need a thermistor.
Yeah, whatever.
Does it need a thermistor or thermocouple? Because there are two different types of temperature sensors.
Does that? I don't know.
Okay, voltage divider and filter. So this is the easy part. You just have to divide the voltage to the scale that it needs. For the input of the chip, and it probably gives you all the calculations that you need to know. To get it done. And fast charge termination, initial hold off period, which is basically saying don't start charging for a certain amount of time for the voltage to stabilize first. Maximum charge time. And this is basically a dead, this is a hard limit of how much time you will let the chip to get charged. And the timing is already done here. You just have to select the right value for the R and the C to give it the right amount of time. So, for instance, if you use a charge rate of 1C, then 1 hour and 30 minutes would be a pretty good limit. Basically, even if there's no other indication that the battery should be charged by now, within 1 hour and a half you turn it off anyway, just by time limit.
Right.
So in this case, you can use this calculation here and figure out what you have flexibility because you can change one or both to get to the value that we want. Okay, so that part is not too difficult. Maximum temperature. Now this is the one that you're talking about. A negative coefficient thermistor. So definitely it says here that use a thermistor, which is basically a resistive device where the resistance changes according to temperature. If it is a negative coefficient thermistor, that means the warmer the temperature, the lower the resistance. Reference to VSS, which is ground, and placed in thermal contact with the battery may be used as a temperature sensing device. Figure 6 shows a typical temperature sensing circuit, which is right here. So you have a we have a thermistor that is inside the battery pack. But when you only have one cell, you don't have a pack, and the temperature is not going to be very accurate unless you tape it onto the battery itself, because otherwise, if the ambient temperature is low, it's going to be low. So I'm not sure whether we want to do this or not, because we don't have an enclosed battery pack, which is what this is intended, to be.
So looking at that diagram, the big one, if it ends up being too large for the pin, could we,
What being too large for the pin?
like the diagram you were looking at that you said was all complicated?
Mm-hmm. Well, that's an overkill. I mean, this picture here,
Yeah.
single cell, lithium ion, 3-cell nickel, cadmium nickel metal hydride, 1 amp charger. So it's definitely overcomplicated because let's see what is in this picture here. Okay, battery in, battery out, we need that anyway. Okay, that's always needed. DC in, we'll need that. And then they have a little bit. Okay, let's see what this circuit is doing here. This is our LED, so that's easy to tell what it does. And then we have a chemistry selector here. So the chemistry selector is an input from outside to indicate whether we want to charge nickel metal hydride or lithium ion, because the two chemistries require a different type of charge strategy. So that pin goes here, which also goes down here. And that's that's one complication that we definitely do not need, because we know the chemistry already. So I don't think our circuit is going to be this complicated.
Okay.
The other thing we could do is let's find out what is the name of this part. It's maybe the part name, but let's go to the top and find out. EQ 2000. Okay, let's go to our browser. Just look for EQ 2000 application, because sometimes they give you application notes, which is different from a data sheet, because it just gives you basically n scenarios of using that chip. There we go. This is the chip that we want to consider. And, oh, you can request samples. We don't have to buy it.
Let's do that right now.
We have so many different people. If each person order the maximum number of units, I think we can probably produce a whole bunch of this stuff without having to pay a single penny.
That's right. Scammed.
And it also has a PDIP version, which means it is easier to prototype with a PDIP version. CAD symbols, related products, technical documents, application notes. Great. Okay. Control fast charge, termination, issues with system load applied across battery. This is not going to be a big issue for us. This is basically while you charge the battery, you're also using it, for the application. High efficiency dual chemistry. We don't need to get too concerned about that. So I think this is the only one that we need. Let's take a look at that. And see where's the circuit diagram. It's the same diagram for dual chemistry. I think you just have to put it together, using these individual pictures, and that's the only thing you have to do. So that means you have to, read the whole document, and then put the circuit, together. So you want to do that? Okay, well, Hardy is the one. All right. So I think we got quite a few components knocked out today. I think we got the IRED driver circuit, we got the voltage regulator, and then we are this is something to be done. But the other two are pretty much all done using the reference circuit in the data sheet. We also specified a few parts, including the inductor, the capacitor, and whatnot. So I think that's good. I mean, this is a good day, efficient use of time. We didn't talk about any software stuff today, because no one was. Well, Jason was here, but nobody else was here, in the software on the software side. Did you guys have a chance to set up AVR Studio?
I did. I messed around with it. I kept on playing with it, and then I got stuck to a point where it's not my fault. It's a simulator. It's broken. But when you put the chip into ADAC conversion mode, or enable it, when you go to sleep, it's supposed to start the conversion automatically, and then when the conversion stops, it's supposed to interrupt, and it does not. And I looked for hours and hours, and I asked on forum, and the guy's like, "Yeah, simulator might be wrong." So I was like,
Can we get it uploaded? like
The,
code?
I was gonna upload earlier on the repository link. You guys know on arcdev there's like
Did that
a
get,
repo man thing.
Did that get finalized?
Yeah, well that's working. But so I'll post it up there and all the other.
Can I-
Are you guys using Get?
What? Huh?
Are you guys getting Get? You know, GIT?
No,
Get?
SVN I think. Chase set it up.
Okay.
Make a suggestion.
Yes.
When you guys finalize something like that, and
Well,
then
he's still working on it. It
well,
works.
when it gets started working, can we get like an
Yeah.
announcement about that?
Sure.
Well, you can connect. I'm pretty sure it chases it up, so it's just the web interface, but you still have all the controls through SVN. It's just the web interface that he's